you've ever tried to burn a hole in paper using a converging lens, then you already know how to find the focal length. Rays emitted from a distant object approach the lens in parallel. These rays all converge to form an image at a distance called the focal length. Experimentally, you measure the focal length by aiming the optical bench out the window or at a bulb across the room and moving a screen in behind until a sharp image is obtained. Distances are easily measured on the scale of the optical bench. You must be careful, however, to place the white side of the screen in the middle of the carriage by having the mounting screw of the bracket on the front side of the screen. Here we adjust the lens screen distance until a sharp inverted image is obtained. We see the DNA statue outside the science complex come into focus. A ray trace shows where the image forms when the object is not at infinity. One ray to be traced begins at the tip of the object, runs parallel to the optic axis, and then dives through the focal point as before. Another easy ray to trace passes through the center of the lens undeflected. Where these two rays intersect is where we expect a real inverted image. For good measure, we can also sketch a ray that passes through the near focal point first and then emerges from the lens parallel to the optical axis. All three rays converge at the tip of the image. The equation relating the object distance to the image distance is that the inverse of f equals the inverse of p plus the inverse of q. Generally, this inverse relationship implies that for objects beyond the near focal point, the smaller p becomes, the larger q becomes. The object used in this experiment is a transparent arrow that we illuminate from behind. We also place an aperture next to the transparency to give a sharper image. As with the screen, position the object on the bracket so that it is over the center of the carriage. This means that the transparency is on the screw side of the bracket. Since you will be measuring a number of object and image distances, one way to speed things up is to note that there are actually two conjugal lens locations that will create an image for a given object and screen location. As an example, here we show an object distance of 10 centimeters and an image distance of 50 centimeters. By moving the lens alone, we see that an image will also form with an object distance of 50 centimeters and the image distance of only 10 centimeters. Place the object near the 0 centimeter mark and the screen at 110 centimeters. Move the lens until a sharp inverted image forms. Record the object position, the lens position, and the screen position. Now, keeping the object and screen fixed, move the lens much closer to the screen to form another image but smaller. Record this new lens position. These pictures show a typical sequence of measurements, moving the lens twice for each new screen position. If we rearrange the lens equation, solving for the inverse of q in terms of the inverse of p and the inverse of f, gives 1 over q equals minus 1 over p plus 1 over f. This represents a straight line when we consider 1 over q as y and 1 over p as x. The slope should be negative 1, and the y-intercept is the inverse of f. Here is our plot of 1 over q versus 1 over p with a linear fit. The inverse of the y-intercept should be compared with the focal length of the lens. A diverging lens, with its negative focal length, causes parallel rays from a distant object to diverge as if they originated at the focal point. A real object, shown to the left of the diverging lens, will form a virtual image also on the left side of the lens. The ray emerging from the tip of the object parallel to the optical axis diverges as though it came from the focal point on the left. A ray through the center of the lens goes unrefracted. A ray headed toward the far focal point emerges parallel to the optical axis. These rays can all be traced back to the virtual image with negative q value. The same lens equation is used, but f and q are both negative in this case. In order for a diverging lens to form a real image, we need to consider a context where a converging lens brings rays to a focus and the diverging lens delays the focus, pushing the image distance further back. This is the case, for example, correcting the nearsighted eye. In this experiment, light emerging from the object is first brought to a focus by a converging lens, lens 1, and forms a real inverted image. The converging lens is now followed up by a diverging lens, which places the final image further back. A good mental model is that the image from the first converging lens becomes the object for the second diverging lens. The tricky part is that this is a virtual object located on the wrong side of the second lens, with a negative object distance. For tracing rays, consider a ray from lens 1 heading for the tip of the virtual object. It is then deflected by the diverging lens as though it came from the focal point. Consider a second ray coming from the first lens and heading toward the virtual object through the center of the diverging lens. It proceeds undeflected and eventually intersects the other ray to form a real final image. By using this combination of two lenses, it is possible to form a real image for observation. Begin by placing the screen at the 80 centimeter position and adjusting the first converging lens until a sharp image is formed. Lock down the converging lens 1 and never move it. This ensures that the image from lens 1 will remain at 80 centimeters throughout the experiment. Place the diverging lens 2 at the 70 centimeter position and carefully locate the final image. The diverging lens is seeing the virtual object locked at 80 centimeters and pushing the final image back. 1 centimeter at a time, progressively move the diverging lens closer to the virtual object and continue locating the final images. Construct a graph of 1 over q versus 1 over p for the diverging lens and expect a slope of -1 and a negative y-intercept with an inverse equal to the negative focal length of the diverging lens. Here is a graph of our data for the negative lens. A concave mirror will bring rays to a focus, as will a converging lens. P is the distance from the object to the mirror. A ray that emerges from the object parallel to the optical axis is reflected through the focal point. A ray that passes first through the focal point will be reflected back parallel to the optical axis. The two rays converge at the image location. The equation for the mirror is identical to the lens equation. Since our mirrors have a fairly long focal length, we need at least 2 meters to work with. Here we joined two optical benches end to end. We place the object near one end of the dual optical bench and the concave mirror at the far end. Please be careful not to touch the surface of the mirror. If we find that the fingerprints match yours, you may be subject to waterboarding. Place the small viewing screen directly between the object and the mirror. Begin with the mirror 200 centimeters from the object and locate the image. We just measured object-image distances with the 2-meter stick. Reduce the object distance to 180 centimeters, then 160, and finally 140 centimeters. A plot of 1 over q versus 1 over p should again be a straight line with a slope of -1 and a y-intercept equal to the inverse of the focal length of the mirror.